We present the machining-oriented framework for converting step milling models into process planning-level manufacturing feature entities. Here is a detailed introduction to this extraction framework. The input is a step model. We first parse the step model into fundamental faces, edges, and vertice. Step 1 is attributed adjacency graph construction. Since conventional dihedral angle methods may become unstable for curved faces, we propose the local transformation-based adjacency inference in detail. For example, we first consider the endpoints A and B of the shared edge between Fi and Fj, wit Qk as their midpoint. Next, we obtain offset points Pi and Pj by moving Qk along the auxiliary directions Mi and Mj respectively. Then, we generate transformed points Pi plus and Pj plus by offsetting Pi and Pj by x2 along their respective normals Ni and Nj. Finally, we perform concavity convexity inference based on the comparison between D1 and D2. Subsequently, we proceed to step 2, candidate region extraction. Since material removal usually produces inward transitions between adjacent faces, we propose the concavity-guided candidate feature region extraction in detail. For example, we first initialize the candidate region a can starting fro, an unvisited seed face Fs. Next, we identify faces F1, F2, and F3 as concavely adjacent to Fs. Then, we recursively add all faces reachable from Fs through concave adjacency to our can. Finally, the search terminates when no additional face can be included, yielding the resulting maximal concave connected candidate region. However, in interacting structures, a single candidate region may contain multiple features due to shared side faces. We proceed to step 3, feature decomposition. We first perform axial projection interval analysis. For example, we first identify two baseline faces, FB1 and FB2, and determine the axial direction AB. Next, we order the baseline faces from bottom to top along AB. Then, we project the baseline faces to obtain IB1 and IB2. Finally, we compute the projection intervals I1, I2, and I3 for side faces F1, F2, and F3. Furthermore, we perform face ownership propagation. We first determine that face F1 satisfies the condition and add it to set A to identify the feature below FB1. Next, we extract a decomposed sub-feature through pocket. Then, we determine that face F2, adjacent to FB1, satisfies the condition and add it to set A. After that, we determine that face F4, adjacent to the faces already assigned to set A, satisfies the condition and add it to set A. Finally, we extract a decomposed sub-feature, blind pocket. Afterward, we proceed to step 4, feature classification. We categorize the target features into 8 classes. For whole features, they are identified by stable surface composition. For other complex features, they are identified based on topology chains. We use blind slot and step classification as an example in detail. The input is blind slot and step model. We first construct the open chain GMS with terminal faces F1 and F2. Next, we observe that at terminal face F1, the external neighboring faces F3 and F4 define two dominant normal direction groups N3 and N4. Then, we observe that at terminal face F2, the external neighboring faces F3 and F4 produce the same two normal direction groups, resulting in Km equals 2 and classification as a blind slot. Meanwhile, according to the same method, we obtain Km equals 3 and classification as a step. Finally, we obtain feature classification and parameter extraction results. An industrial CAD model containing multiple manufacturing feature types is used as an example. It has 41 feature instances. Among them, a 39 is used as an example in detail, including category, machining direction, baseline face, boundary chain, depth, radius, and spatial extent. We present more feature recognition results as follows.